All right, thank you. Thanks for the introduction. Thanks for the invitation. It's a great pleasure to be back in this room and speaking with you guys. Um, so I get right to the main elements that I'll be covering. So stochasticity, of course, is one of the elements. So as also the title says, stochastic hybrid uh, I think I didn't put multi-agent in the title, but okay, so the third one, but that's the expertise, the local expertise. But so as a mechanical engineering, trying to mention how stochasticity enters, I think this is a good example that shows, uh, the tire friction on this car is just going from stick to slip in random patterns. And as a matter of fact, stochastic models, stochastic differential equations or difference equations are very well suited models for the study of these things. So we can also consider the effect of winds, but we see the same system later on. So just in the next slide. So the second element is the hybrid aspects of things. So for instance, changing the gears in a car, and this is as a project I did at McGill right here with Peter. And this is something new. Just this is a drone that can also sail, so it flies in the air and also, also sails on the water. Okay, and as you see, the system is switching between different modes. So the last one doesn't require any introduction here, right? So multi-agent systems are, are very frequent in systems and control theory discussions. And I'll try to, in the last part of the talk, I'll try to get to the multi-agent and particularly the mean field systems and games in the top. Okay, and also I remember that these seminars are supposed to be informal. That's still in the title, right? So please feel free to ask during the time, during the talk. I'll be happy to share. Okay? There's no formal structure to this, but an element in the title was fixed terminal state or something I put in the title, right? So in certain engineering applications, as one that you see here, we have very precise requirements for the state of the system to occur at certain times or at certain desired times. So for instance, in the landing of reusable rockets, the system is required to come to this landing platform, okay? And as you can see here, some user used all the videos that SpaceX releases and found the points of landing from the videos, okay, of the successful landings at different times. This is 2019. There's no update because, just a fun story is that they don't release the data, but they release the videos. So this is through a video analysis. But anyways, so the point is, the rocket is required to come at certain locations, okay? So all the components of the location are components of the state at upright configuration, okay? All angles are fixed, and also all linear and angular velocities are required to come to full stop, right? So to zero values. So we have desired values for the state of the system. Otherwise, the results could be catastrophic, right? So if these requirements are not met fully, so lots of billions of dollars will go to waste, right? So the question that I'm trying to address here is, in the presence of stochasticity, how should we look for these specific requirements to be met? How do we fix the terminal state so that in a stochastic world, so that the system meets the desired requirements? Okay, so just some background of what has been done in the absence of any constraints. So we have, and for systems which are generally nonlinear, there are multiple versions. That's the classical stochastic optimal control, including the stochastic minimum principle, stochastic dynamic programming, and comparatively less explored convex duality approaches. Okay, but in the presence of certain forms of constraints on the state of stochastic systems, the discussion was mostly only for linear and linear system quadratic costs and Gaussian desired distributions for the state. Okay, when the system is linear, lots of simplification or lots of interesting structures emerge that we can use. For instance, if the state is Gaussian, then it remains Gaussian, right? But not for nonlinear systems. So this is one of the things that will be addressed here in the nonlinear extensions. But just for constraint and nonlinear, there are few studies, and most of them are very recent. So there's either iterative linearization, so that we meet, so we use the linear models, but in an iterative manner, we try to get to better and better satisfactions of the requirements. There is the use of feedback linearization to, again, enable us to get to and use the LQ results. But so there is the nonlinear Schrodinger bridge, which has some connections to the discussion that I'm presenting, but there are limitations to this model. For instance, the drift in the dynamics needs to be the gradient of some potential function, right? But for general nonlinear stochastic systems, so two ideas that I've been working on was the terminally constrained stochastic minimum principle, which I'll be presenting in the first part, and the convex duality approaches that will be in the second part. Okay, and these methods are descendants on the unconstrained stochastic minimum principle and the unconstrained convex duality approaches that were established earlier. All right. Okay, so that will be the first part. I'll give a pause in case anyone wants to ask questions. Otherwise, I'll proceed. All right. Okay. So let's revisit the deterministic problem first. Okay. So we have a deterministic system, nonlinear, with the initial state. Okay. So the fact that I'm putting t instead of t0 is that we have, so state is, this is what I learned from Peter, is that state is a perpetually renewing initial condition, right? And especially when we get to the dynamic programming decomposition, which I learned from Aditya, so we can decompose the problem into these steps. So essentially, the initial condition will be given or will be known at time t when we are doing the dynamic programming decomposition. Okay, but now we have also a fixed value for the terminal state. Okay. So for these types of problems, we can use the minimum principle. right? We can find the optimal input as the R mean or R inf of the Hamiltonian defined in this way, which has this adjoint process as its component with this dynamics. But because the terminal state is fixed, then the terminal value for the adjoint will be free. Okay. We can also, sorry. So, we cannot use dynamic programming for problems with fixed terminal values. Okay. And the main issue is that even if we can show that if a value function exists for this problem, it satisfies the HJB equation. There is no well-defined form for the terminal or for the boundary conditions of this PDE. So we have a singular PDE because the terminal cost must be zero if the state satisfies the requirement, but then nothing else would be an answer. So, one way to present it is to say that the value function is infinity at every other point. Okay, so we are dealing with singular dynamic programming. So dynamic programming doesn't provide us any particular answer, but convex duality approach that I will be speaking later on will help us do that. But before getting there, let's just look at this answer of, okay, so now the system is not deterministic. We have a stochasticity, right? So we have the linear process interacting with the system, and we are trying to minimize in the dynamic programming. Now we also are looking at the conditional expectations. That's the shorthand notation of given the filtration at time t, right? So the condition, so xt will be deterministic under the filtration at time t, right? So we know the value under the assumption of complete observation of the state. Okay, so I have to be, usually I don't have to be this careful, but I have my teachers in front of me, so I have to be also very careful with these terms. But so the main question is, in a stochastic world, how do we quote unquote fix a value into the future? If I put xtf equals some desired value, that will violate causality in the system. So I'm imposing a non-causal constraint on the system, right? So the big question that comes is exactly how do we constrain the terminal state with the motivations that you've seen, right? So I have a reusable rocket, okay, and I want to land it with precise requirements. But how, if I want to work with stochastic systems, how do I model that, right? So one way that this is the work that I've done at Georgia Tech. So one idea is to enforce a constraint on the conditional expectations of the terminal state. Okay, so if mu f is the desired value, I'll impose an expectation constraint. But this has been at least wasn't that unanticipated, but the novelty lies in the fact that we are renewing this constraint under every filtration, right? So it's not just under the initial filtration at T0, okay? So we're not looking at the total expectation. We're looking at the entire family of conditional expectations, and we are imposing the constraints on that, right? And as a matter of fact, we can show that there exists a version of the minimum principle, of the stochastic minimum principle, which we call the terminally constrained stochastic minimum principle, that with the same format for the Hamiltonian and the same dynamics as the unconstrained version. Yes.
So is this constraint stronger than what you initially wanted, or is this equivalent to the just the terminal constraint?
So it is, I'd say it should be weaker, but this is the strongest that I can think of that we can impose. Because as you will see, although I don't have a formal proof for that, but at least through some examples, I can show that we get to the almost surely satisfaction of it. Although we are not imposing the almost surely satisfaction, right? So the second or the best option for us, the best non-causal option is to write just XTF equals or almost surely equals mu F.
No,
right?
So maybe let me rephrase, right? So if you look at the terminal time,
right?
You are taking the almost sure constraint
yes.
and replacing it with a constraint that should be met in expectation.
Right.
So that's a relaxation.
Yes.
But now you are saying this expectation constraint should be met at during entire trajectory as well. From the relaxed version to imposing the constraint on the entire trajectory, is that an additional constraint or?
That's challenging to put into words, right? Okay. So essentially, but let me just give this extra explanation. I hope the online audience can also see what I know. Yeah, so green is not the best one, red is. Okay, I remember that. But okay, so this is time t, right? Yeah, I'm an expert in 437, right? Okay, so at time t, this is mu f, right? So there are realizations, okay, of this state, okay, and all I'm imposing at time t is just that once I get to the distribution here, okay, if you have blue or black, it will be readable, but okay, green will be difficult, but at least I need two colors, right? So if this is the probability distribution, all I'm imposing is that the expected value matches the desired. But the novelty is that, so if I only do that at t0, then I still get distribution. So I'm not satisfying the constraint. But if I keep doing that for all t, and that would include all t that are getting closer and closer to tf, right? So as I get to tf, right? So I'm still having a distribution, okay, that will do that. Let me show. Okay.
No,
right. Okay. All right.
Yeah, I think that's okay. So, yeah.
Okay. All right.
If you take it as a random process, then is that a martingale? So do you have a kind of running martingale constraint?
Yes, there should be, I guess.
It looks like a martingale to me.
Yeah. I know people that use the martingale representation theorem on an equivalent problem, but yeah, I haven't examined it. Okay. Yeah, but yeah, it's an interesting way to look at this. But yeah, if I do that, then we can prove the almost surely satisfaction. But yeah, so right now this is just the suggestion. But and let me not raise the expectation too high. There would be some implementational issues, as then we need to use large values of input to satisfy the constraint. So it is costly to impose this, but we still get. Yes.
Ali, may I ask a question?
Absolutely.
Along the same lines, it seems to me that if you just were concerned with minimizing cost up to a certain time in the future, so irrespective of the terminal condition, And then once you get to that time, you can start imposing the expectation equals
Yeah.
0 result. It would seem to me it would be less demanding, but it would still meet your constraint.
I'm very glad that you asked it,
Okay.
because you'll see in 2 more slides a relevant, not exactly what you described, but a relevant idea that will happen. So indeed, this is a CDC paper, CDC 2021 or 2022. I have the reference there, but yeah, thanks. Yes.
Okay, sure.
I've got one more similar question. I noticed that, like, in your description, you constrain the set of inputs to being within the set U. How does this method like handle situations where a particularly bad disturbance just pushes the reachable the target outside of the reachable range of your control? Like, you're landing your rocket, but there's a sudden unpredicted 40 mile per hour wind that just pushes your rocket to a bit too far to just maneuver back to the launch pad with the given
What's the
fuel.
probability of that? It would be like, so this is very, so that's the almost surely part. So there still be realizations, but the total probability of that happening will be 0, right? So that's the almost surely satisfaction of
Yes,
this,
but
right?
as you get closer and closer to the target time, wouldn't the probability that, since you're trying to hit this expectation at and your range of motion is being reduced over time, isn't there? It doesn't seem like it would be almost surely the case that you can actually always touch down on precisely onto
Almost
the target.
always, right? So not always. Yeah.
Almost always.
Almost always. And that's exactly that. So the winner process, so we are interacting with the winner process, and our axioms of, for those of you taking, forgot the number, 509, or, the stochastic processes with Peter, you see the axioms of the winner process, right? So one of the axioms is that, so we have the expectation, the expected value is 0, the expected value of it, times itself will be, dt and so on, right? Yeah.
So one thing here is your filtration is controlled.
My filtration is controlled. What do you mean by that?
Control event.
It depends on your control policy.
So this is a restriction on the set of admissible inputs, right? And indeed, as I get closer to TF,
because I can have a terrible control law, and I'll never meet this, right?
Yes. So indeed, earlier I will put superscript U just to emphasize that this is given the input policy, and then this is the restriction on the class of admissible inputs. And indeed, as T gets closer to TF, with some, let's say the input set is compact, then we could get just empty set, that set could be empty. So the challenges would remain, but also, as Roland mentioned, at least as we get very close to TF, then we don't need to impose that constraint.
Actually, as chair of the meeting, having to land you target time near the end of your talk.
All right, yes.
We've been discipline ourselves because we're having too much fun.
All right,
slide 7 already.
Yes,
so
all right.
We've got to land you.
Okay, all right, yes. I will be happy for any follow-up discussions, either today or at a later time, okay? If any of you are coming to ACC, I'll be also available there. But also I'll be available over Zoom and so on, right? Okay, and just let's see what happens if I do this for linear systems. Okay, so I have linear dynamics and I have quadratic cost, just forget more analyticity, because I'm providing analytic solutions, let's just forget about the Q terms and just, we have the minimum control effort type of problem. So, and I'm imposing this constraint on the linear systems. Indeed, we can find a closed form expression nicely represented in terms of the state transition metrics, the controllability Gramian between two times. Okay, so usually this is from T0 to TF, but if we just extend the concept to any two times, okay, then the solution will be just in terms of the state transition matrix, controllability Gramian, and the Riccati matrix. Okay, and notice that T is the filtration. Okay, so T is the filtration, and S is just a time that runs from the current time T to TF. So I get an adjoint value, and then as you know, it's just the optimal input is just R inverse B times that, right? B transpose. But so everything is computable, and we can just simulate. So for some examples, we can simulate just with one-dimensional linear process, with just one component being influenced by the linear process, and two. Okay, the distinction of these two is in the dimension of the input, right? So as you see, we have one-dimensional input and two-dimensional inputs, okay, for similar system. And as you see, almost all trajectories, that is those simulated, satisfy the desired terminal distribution. These are the components for better reference. Okay, so this is the 3D view. These are the components. But as I mentioned, in here, as we get closer and closer to the terminal time, the probability of having to use large values of input increases. Okay, and this is for the unconstrained input, right? So my input value set is the entire RM, but if let's say the problem was just bounds between minus 100 and 100, then you see that we have inputs that go beyond, so we cannot use it. Therefore, those inputs are not admissible. So we get the admissible value set will be zero, empty, right? But so now getting to what Roland mentioned. So now we can look at it in certain ways. So I looked at it as the information structure. So assuming that I don't have exact observation of the state at every time. Okay, so this is the continuous in time exact observation was the one that I presented, but the second item is that I can only observe the exact value of the state at discrete times, right? So at certain times, let's say just every 0.1 seconds, I can observe the exact value. Therefore, I can only impose that constraint under these filtrations, right? Or I have exact observations. So the results that you see, this is just the exact observation, continuous exact observations of the state. Okay, this is observations every, I guess, 0.01 seconds. Okay, on an 0 to 1 interval. Okay, and so this is empirically, I cannot show that this is delta distribution, but if we do a very good simulation, we get delta distribution here, but we get some Gaussian distribution with non-zero variance. And if we just do the intervals to be 0.1, okay. Oh, I remember this is 0.05, this is 0.1, right? So every 0.1 seconds, we get this distribution. And if in addition, we also have a noisy observation of the state in continuous time, then we also need to look at the Lyapunov equation for the filtration, okay? And now the only difference is that x tau, so x tau is the most recent exact observation of the state, and x hat here is the, so x hat in here is the estimate coming from the Kalman filter, right? So that concludes only the first part. Okay. All right, so I'll try to be more quick, but as you remember, dynamic programming led to a singular HAB equation, right? So with singular boundary conditions. But okay, so let's see that I'm not imposing a delta distribution, but now I'm imposing a probability distribution. I'd say that I want the probability distribution, given the input u, right? The probability distribution of XTF belonging to any Borel set is just the integration over that set of a desired probability distribution. So PD is a desired probability distribution, okay? So this is a less precise but more understandable, is that XTF is distributed by PD, right? And so again, we have the same dynamics. Now we get, this is, some of you have seen this, but this is like CDC and LCSS 2022 of now identifying a value function type function, okay? The distinction is that, so this is, forget about the inequality for a second. This is the HAB equation, but instead of identifying the function from just its value at t0 and x0, we need to identify it from the difference between this value and the integration of the terminal value, again, integrated against the PD. In other words, it is as if we have an HAB equation with free terminal conditions, but among all potential terminal conditions that we can impose, the terminal condition that maximizes this difference is the one that identifies us the value function, okay? And let me show it with an example. So I'll skip the sketch of the proof for a second, okay? And this is how it looks. Just for a linear system, okay, with just the control effort as the total cost, and the desired distribution, which is Gaussian with mean at mu d and variance with sigma d, okay? We get this Hamilton-Jacobi inequality. If I plot among, and let's say, I know that this problem must have, given the literature on the covariance steering, we know that we can use the Riccati equations. So I know that the value function is quadratic, okay, for this problem. So all I do is that I change the terminal conditions, so the coefficient, so this is gamma, h gamma x squared, right? So 1/2 plus just mu with the, just, this is the quadratic equation with mu. So if I do that, mu and gamma, right? So if I plot different values of this difference, okay, you see that there is a maximum here, right? So the maximum is right here, okay? There are values that maximize this difference. And if I plot the function, this is the function for, this is the value function for this problem, okay? And indeed, if I use this value function, okay, these are the realizations, I guess is 200 or 100 or 200 sample paths. You see the empirical distribution matches the desired distribution So this is eventually exact, but with 200, this is pretty good, right? And let's say that instead of that distribution, I need just a mixed Gaussian with two different means, right? Then again, and sorry for this spacing, okay? But so now what happens is that with parameterizing these, so with these test functions, and the format, indeed, I borrowed from Roland's paper on a different topic, but if we look at this form of a softmax, soft mean, sorry, so soft mean of two Riccati equations, okay? And then we parameterize them by these values, okay, and also the terminal conditions for Riccati equations. Then we see that for one of the parameters, which is gamma, is the weighted. So this, you know, for this one, we never get the supremum. So the supremum is never achieved. So it's not a maximum. Okay, well, no, yeah. So the supremum exists, but it's not achieved. So it's not a maximum, right? So it needs to go to infinity. But if we look at the equivalent function, is just the mean of two quadratic functions, as you see here, right? And indeed, if I use this as the value function, the trajectories exactly do that. So the empirical distribution matches eventually perfectly, but you know, with 200 sample paths, just you know, with good precision, the desired distribution. Okay. All right. So I'll pause for a second.
Andy, can you
Yes, Mini.
can you just keep this page? Here you have the HG inequality, and then next you have the test functions. So what's this V sub gamma? What's the relation between this V sub gamma and the value function?
Okay, yeah. So I was trying to escape this part because of time limitations, but now that you asked, I'll mention this. So the fact is that, so now let me go back. So, all right. So as you see here, this is the capital V is the value function, is the true value function. But the small v is now, so now this is the way that the convex duality approach works, is that now we have a supremization over all C2 functions, over twice continuously differentiable functions, satisfying this inequality, okay? And that contains all solutions to the HJB equation as well as others, right? But now we have these differences. So now this is a search, this is an optimization in the space of C2 functions. This is a very large space to explore. But the way that these examples are solved is that now I'm restricting the search in certain classes. If I know for some reason that my solution also belongs to this class, and then if the maximum exists, then the maximum value that achieved will be that maximum value that I desire because it was in this class. And if it doesn't, then the supremum value will identify that. That's how these test functions work, and these gammas are just a set of terminal conditions. So here, just in this plot, gamma is just eta, which is this parameter in the denominator here and the in the exponents here, right? So that's the soft mean. And the other one is H gamma, which is the cost for the Riccati equations, the terminal value for pi in the Riccati equations. Okay, and among this, and I can do that for larger values too, but just for illustration purposes, this is for that. So we need to do a search in the space in the infinite dimensional space of continuous functions, just or C2 functions, twice continuous differentiable functions. But we restrict the search by looking at these subclasses, and then now the search is over these parameters. Did I answer your question, Mini?
Yes. So you search from this space. Is there any justification that this is a good class for you to look for? You use this particular construction.
All right. I refer you to Roland because I borrowed this format from them. I'll be happy to do a follow-up after this talk, but let me finish that part that actually I need your expertise on this.
Okay, go ahead. Yeah.
Okay.
Thank you.
All right. So I'll skip, as a matter of fact, for the interest of time, I skip the stochastic hybrid systems. Okay, this is the work that I've done at McGill. All right, this is years of publications with Peter on the hybrid deterministic and stochastic hybrid neural principle with this terminal condition or the terminal constraints added with my work with Panasiotras. And so again, this is for the car, this is for the drone. Just I quickly play these videos. All right, so they don't, okay, needs permission, but okay, I'll skip the stochastic part. But just okay, so I'll just stay here for a few seconds just to show that we have a controlled switching here. And as you see, the control switching can happen at every time, at any time, and any state, okay? And for different realizations, we have different switching times. There's no particular structure, but each of these switchings are optimal, okay, for the realizations that are happening. But I'll skip that because I want to get to the local expertise on the last part, at least to get some material for the follow-up discussion, okay? All right, so the multi-agent systems, okay, mean field and graph, right? Okay, so now this is your work with Peter, also Xuan, also many others in this room and in the online audience, right? All I'm adding is some form of constraints on the probability of agents. So for this, this is a very recent work. As a matter of fact, just one paper submitted. The fate is unknown, right? But hopefully, with discussions with you guys, we get to explore this idea further. But so we have a finite population over finite network, okay? With the standard dynamics, all I'm imposing, and for this purpose, because we have a probability desired distribution, I assume that they are, as part of a team, they are not playing against each other. They are collaboratively trying to minimize this cost, okay? Although you probably know, but I emphasize it later. But they are all trying to minimize this cost, and at the same time, they are trying to make the probability distribution of each subclass to a desired probability distribution of their own class, okay? And the index I that appears here is just coming from the fact that we are now in the decentralized way, we are trying to do a member by member optimality to achieve the team optimality, all right? So all these steps, it's just the translation. So these are standard from, I did a precise restatement of Mini and Peter's paper, Sion paper in here. I doing minimal changes to the notation, but I'm just translating the desired probability distribution, okay? And I'm going and doing the the same translation, the convex duality approach towards that. So again, we have the HJB equation, okay, and the inequality one part is just, I note this, that one part is coming from the fact that so when it is positive for all values, including all values of input, then for optimal input, it will turn into 0 almost everywhere, right? So that's one of the justifications, but it also holds for other reasons. So it also includes non-value functions for that matter. But as we do, okay, now the one that we should be looking for, so instead of solving the HJB equation, now we are solving an optimization problem over HJB equations, okay? And the Fokker-Planck equation, very similar to the unconstrained case, and also the optimal policy, okay? So these are the standardized by local expertise format of presenting, except for the fact that now the HJB equation is turned into an optimization over family of HJB equations, okay? And so again, I skipped the proof, okay? For linear quadratic Gaussian networks, then we can use Schwang's, and Peter's iterative so we can do an iteration on the work on the LQ case, okay? So we just start by assuming a terminal condition for the value function. Then we use their method for the unconstrained case. And then we do this, we compute this difference that we want to maximize. And then we update we do some updates in an ascent direction for that cost, okay? And indeed, for just this is for a cluster of 40, so 40 clusters, and I guess 20 each, or no, 20 clusters, 40 each, I guess, agents. I have the paper, but for the matter of discussion, we don't need to do that. But if we look at the evolution of the states, so they all start from the same distribution, and the total population's distribution will reach to the desired probability distribution at the end. I guess this is so I'll leave it here. I'll open the floor to more discussion, and as I mentioned, I will be happy to chat with you guys in any setting. All right.